This podcast is brought to you by LMU Munich.
Thanks. And as, of course, all the lectures in this school, we're to be talking about methods that have been developed in the last decade and a half for computing in field theory and particularly in gauge theories. But this first lecture, or much of this first lecture, I'm actually going to devote to sort of a review and context and things that are not directly the new methods themselves, but to it's also an opportunity for me to get to know a little bit about what your interests, what your background, what your what level you are in your studies. And I will say that basically maybe starting tomorrow evening after my lecture tomorrow, I encourage you, those of you who are interested in perhaps pursuing thesis topics and who haven't yet started a thesis in one of the areas in the list, encourage you to come and chat with me if you want ideas or if you want a little bit more guidance in things you should read or things that you should study, things that I think might be good things to think about. I realize there's some people here who are relatively young on the academic scale, and so some of the things that I'm saying should be review today may not be review. I can't help that. I hope that some of it will provide a first taste then. On the other hand, there are also people in the audience who know everything that I'm going to say in all 4 lectures. So for you, I hope you won't be too bored. So let's look a little bit at some of the motivations. Okay. Motivations and connections for these new techniques. So we have, of course, particle physics, and in particular calculating in the standard model. And at least to date, and probably for the foreseeable future, for reasons that should become clear to those of you who don't already know, it's going to talk about calculating in the SU3 in QCD. There's also connections with the n=4 supersymmetric gauge theory. There's connections. I wouldn't say it's an active area of research anymore, or at the moment, but there's certainly a lot of ideas that are continuing. And then there's a continued use of twistor space in a lot of different contexts. I'm not really going to talk very much about that, but I assume that Freddy Kosower will probably say some things. And here, I expect, will also tell you something about Grassmannians, which is another important connection of these techniques. And finally, there's also connections to n=8 supergravity and the search for finiteness in supergravity. And that's something which you'll hear a lot about from John Joseph Kosower. So before we go any further, I'd like a show of hands. Who here is either doing a PhD or has done a PhD and is now doing a postdoc or is thinking about doing a PhD in something connected to QCD? Okay. Who is thinking about doing a PhD or doing a PhD or has done a PhD and is working on n=4 supersymmetry? Okay. 1.5 people. Who's working on twistor strings? Okay, all right. So there is someone out there, brave soul. And what about Grassmannians? Okay, I guess Freddie has his work cut out for him. And how about n=8 supergravity? Oh, I hope that John Joseph, if he asks the questions, sees some hands raised. Otherwise, he's going to be very disappointed. So today, and we're going to get through I hope, at least all the review material. I guess I should leave the left-hand side of the blackboard alone here. So this is kind of an outline of the full set of lectures. And today, as I said, a lot of the material that I'm talking about as review may not be review to everyone. I'm sure the QCD people, it will in fact be review, but maybe some of the more formal people it won't be. Don't worry about it. Just try and get a flavor of the context. So we're going to talk a little bit about jets, about QCD and the Parton model, about what it means to be doing radiative corrections, about the infrared issues that arise, and finally, I know that Pier Paolo in this morning already taught you everything there is to know about spinor products, but for those of you who might have seen it for the first time this morning, you have an opportunity to get an instant review. We'll then start to look at on-shell methods, and we're going to look at the BCFW recursion relations. And we'll sort of do a lot of looking at the underpinnings of the unitarity method, even things that are not necessarily the tools that you want to use today. We'll look at unitarity, at integral reductions and bases, and finally at generalized unitarity and numerical unitarity. Yeah, I guess I can shift this up a little bit. Actually, how far down can people see in back? Which is the last line that, that people in the back can see? Is this line visible? This one? No. Okay, so let me erase that. And I'll put it up here. In fact, let me put both of these lines up here. So most of what I'm going to say will be devoted to unitarity at one loop. If there's time, then then I may tell you a little bit about more recent developments at two loops. Also, I should say if there are questions at any point, please raise your hand. And if I'm feeling it's a good point to stop, I will. And if you feel that I'm not stopping and it really is essential, then bang on the chair in front of you. So let's start by looking at jets. How many people here have seen pictures of events from the LHC? How many people haven't? Okay. Then let's look a little bit not at the LHC, but to go back to the Tevatron. And these are really the basic objects that we're going to be having, at least those of us who are doing QCD, at the backs of our minds for in any calculation that we're doing. So if you were to stare down the beam pipe at CDF, well, these days it would be relatively safe because the accelerator is not running anymore. But if you were to have done that while the accelerator is running, you'd develop cataracts, so it's really not recommended. But you can let the computer tell you what it would look like. There's the inner tracker, and the structure, of course, of the LHC detectors is very similar. And a typical event has large numbers of tracks, and then there's energy deposition in the electromagnetic and in the hadronic calorimetry. And these things tend to clump into specific angles, and this is a crosswise slice of the detector. So this is now looking at the beam axis over here. There are certain places where we get more clumping of energy than in other places. And of course, these are streams of hadrons that are coming out of the event. Some of them are charged, some of them are neutral. And there are a lot of pi zeros. The pi zeros are going to decay very quickly into 2 photons, and that energy is going to be deposited in electromagnetic calorimetry, not in the hadron calorimetry. So we're looking for jets in all these 3 places. And one of the critical issues, of course, is how to measure those jet energies precisely. So again, if we go now to the LHC, then this is taken from Atlas. Again, we see there are these collimated streams, and they're showing up in the tracking, in the electromagnetic calorimetry, and in the hadron calorimetry. And you can sort of see by eye that, let's say, this is might qualify as a 3-jet event plus I think a muon in this case. And we can see events. It becomes a little bit clearer if we now take the detector, take this longitudinal slice of the detector and unroll it. And this is kind of the right way to be at least thinking about it initially from a theorist point of view. So this here, I guess, is in fact, it's not, I can't tell which axis is which here, but I think this is the rapidity axis, and this is the azimuthal axis around the detector unfolded. And you see all these various circles surrounding these towers of energy. The vertical scale here is the energy that's been deposited in each of the towers, the sum, I would guess, of the hadronic and electromagnetic calorimetry, probably corrected using information from the tracking. Now, that's what the jets, of course, look like from an experimenter's point of view. The thing that's really important to keep in mind for everything that we're doing is that we have lots and lots of jets. So we're looking here out at, by now, a small fraction of the data that's been collected. And we can see events out to, even at the time, beginning of 2011, we had events out to 10 jets. And by now, that has pushed further, probably about to 11 jets. So this is not something where we can be satisfied, in principle, with calculating, from a theorist's point of view, calculating things that have 1 jet or 2 jets, things like that. We really need to be thinking about a lot of jets at the same time. Can we have the lights back on? Thanks. So what are we going to be doing with the standard model at the LHC? So one of the important things to do, let's say if you're going to start with these events where you have low statistics for multi-jet physics, we need to calibrate and demonstrate that we understand the detector. This is we here really being the experiments. And that's in some sense something that is an ongoing process because you're trying to improve your ability to measure. You're going to new luminosity, higher luminosity, you hope, with every new part of the run. You're also increasing the energy. We went from 7 TeV to 8 TeV this year. There's going to be a 2-year shutdown. The hope is to go to 14. Maybe it'll only be 12 or 13 after that shutdown. And of course, the experimental complications of higher luminosity are also increasing. So there's a continual need to demonstrate an understanding of the detector in that new experimental regime. And part of that, an important part of that for doing precision physics, is to understand the jet energy scale. Now, beyond that, once the experimenters have demonstrated that they understand the detector, and part of the understanding of the detector is to demonstrate that they're really reproducing what we know about standard model physics. And that means measuring a lot of things that are old, known, well understood physics from a theoretical point of view. Of course, how well understood they is, that depends on us, on the theorists. Beyond that, we're going to start looking in various corners of phase space. We're looking, of course, for new physics. So you want to look for SUSY, or you want to look for large extra dimensions, or for evidence of new strong interactions. And you're going to be looking in corners of phase space that may have a lot of jets, but you're also insisting on a large total amount of energy. And in those corners, you're going to have backgrounds from the standard model. And our role, of course, is to make sure that we can predict those backgrounds as well as possible. So that's something which is an ongoing process at the moment. It played a role, of course, in the discovery of the new heavy boson, which may turn out to be a standard model Higgs. In fact, I would probably even bet money on it, but may not be. And that's something that has to be determined experimentally. Finally, something that I think will play an increasing role, and those of you who are about to embark upon a PhD, that's something maybe even to think about and to focus on, is the issue of doing precision measurements. To look for deviations from the standard model. And of course that has to be accompanied by precision calculations. So here we're looking, for example, at deviations for the new heavy boson in its decay modes, or in production, and of course for the top quark. And in that light, one of the things, for example, that would be interesting to keep track of is this asymmetry, which may or may not have been discovered at the tevatron. Of course, as luck would have it, it's precisely the kind of quantity that's much harder to assess at the LHC. Generally, things to keep in mind, of course, is that new physics is rare physics. It's almost by definition, because once we find a way of making new physics plentiful, it becomes old physics. It becomes a standard candle. So if you think back to the handful of W's and Z's that were first found when most of the people here were still toddlers back in the 1980s at CERN, that's now a standard candle. It's a background. It's something that you can use to measure the luminosity. And it's good just to keep in mind some of the orders of magnitude that we're fighting here. So if we look at, and this is a slightly old version of the transparency, so of course we don't have the mass of the new heavy boson dialed in here. But if we think about sort of two jets with B's production, that's something that's very common, although it's already a couple orders of magnitude down from minimum bias for measuring the total cross-section. We go down to other sort of boring, old, well understood physics, just the total production of W's and Z's. That's a couple of orders of magnitude down to these lines over here. And if we want to look for the top quark, which is something that's known physics, but something that we haven't been able to study in great detail yet at the Tevatron, there's a few orders of magnitude down. And the new heavy boson, the thing that would like to be the so-called Higgs boson, is another order of magnitude and a half down. And finally, if there's going to be supersymmetry or other physics or whatever, then that's going to be another order to 2 orders to maybe more orders of magnitude down on the scale. So that it means that it's fighting huge, huge backgrounds. And some of these, of course, are kinds of instrumental things that theorists might not even think about, where you lose things inside a crack in the detector, and so you think there's missing energy when there isn't, or things convert and you think you have a lone lepton when in fact you just have a rare jet fluctuating into a single pi plus, things of that sort. There's a lot of things of that nature, but there's also a lot of standard model backgrounds. And one example that one can think about is looking for the Higgs, just the Higgs alone from glue production in the BB bar decay mode. And that's, in fact, the dominant decay mode given if it is, in fact, a standard model Higgs at 126. But you can see that it's just hopeless because you're fighting 6 or 7 or 8 orders of magnitude here. So any sort of rare thing that causes a fluctuation in the QCD background to 1 part in 10 to the 8th is going to wipe out your ability to see that directly. Doesn't mean that people are not going to look for that decay mode, but they're going to look for it in associated production when you have a W off-shell W that produces both a Higgs and a real W. The W in turn will decay into a lepton and neutrino, for example, an electron and its neutrino, or a muon and its neutrino. And the Higgs will then decay into BB bar. So now the background that you're fighting is production of a W in association with 2 jets, where one of the jets at least is tagged with a B. That's something where you actually have a chance, especially if you can think about resolving the mass peak. Well, resolving the mass peak depends on your ability to measure the jet energy very precisely. So we come back to this question of one of the basic aspects of understanding the detector, namely understanding the jet energy scale. It all feeds back into your ability to look for new modes and look for signals. Another thing that you find is that typically you have very complex decay chains that are produced, for example, in supersymmetry. You might have decay chains that produce gluinos that then have long, let's say, pair production of gluinos that then will decay into standard model particles with a long decay chain. And these will yield events that have signals of missing energy from the lightest superpartner along with 3, 4, 5, 6 jets. And so there are standard model backgrounds, of course, which come from Z production, for example, plus 3, 4, 5 jets. And there are, of course, all the instrumental kind of backgrounds that I just mentioned. But these are the kinds of backgrounds that we need to understand. And these are the kinds of things that we can give our experimenter colleagues a handle on as theorists. So how does all of this how do all of these jets look like from a theorist's point of view? So in the real world, what we've seen, so you send in 2 protons, and out come these collimated streams of hadrons. But what we're expecting is that the underlying physics, the short distance physics, is described by perturbative QCD. Short distances, of course, meaning large momentum transfer, or in the case of hadron colliders, large transverse momentum. And if we're working in perturbative QCD, what we're actually doing is scattering quarks and gluons, which are the constituents of the proton. And we're producing quarks and gluons. And so the question is, how do we make a link between these 2 pictures? And in particular, how do we define jets at all? How do we define jets in experiment? How do we define jets as theorists? How many people here have already seen the Jade algorithm, seen the anti-KT algorithm, the KT algorithm in either courses or in their reading? Ooh, okay. So maybe we should spend a little bit of time on that. So what we want to do is we want to take these streams of hadrons, and at the LHC we might have 30, 50 hadrons in a jet. Clearly, we don't want to go around trying to calculate the cross-section for producing 50 particles that happen to be going in a very similar direction, because if you shift them slightly, I mean, just think about the combinatorics of and the complexity of some 50-dimensional distribution. I mean, you'd never even be able to write this down. So what we want to do is we want to map those streams of hadrons into an object. And as we'll see later, there are theoretical reasons for the ways you do it and for the fact that you're, in some sense, forced to do that. And the oldest, and I think conceptually the simplest algorithm to understand is something called the Jade algorithm. It has a number of defects from a theoretical point of view that mean that it's completely obsolete. So people will not use it in E plus E minus, people will not use it in hadron colliders, but it's conceptually simple. So the idea is that we start with some number of particles in the final state, and we define a resolution parameter, Yij, just in terms of the invariant. And S here is the center of mass energy in E plus E minus. So we do this for all pairs I and J. And now we look at the smallest Yij. And we ask the following. We have a resolution parameter, which we can call, is I think traditionally called Y min or Y cut. And we ask, is this smallest Yij less than Y cut? If so, we combine I and J. We combine the momentum. We remove I and J from the list. And replace them with Kij. So now we've reduced the size of our list of particles by 1, and we just keep iterating this thing. It's very tedious to do if you're a graduate student, if you're sent off into a room and given a list of 1,000 particles and told to go off and do this, but it's exactly the kind of mind-numbing thing that a computer will do, and we just iterate this procedure. And at the end of the day, we'll end up with a short list of objects, especially if y cut, for example, is let's say typically a third, or maybe it's a quarter or a fifth, something like that. If y cut is 10 to the minus 7, then yes, you're going to end up with a long list of things. But if it's not too small, you're going to end up with some short list, and those objects, those momenta, are the jets. Now, this, as I mentioned, has a number of bad properties as far as resummation, and as far as the jets that it produces are not really the things that you would tend to identify as jets in a detector, but that's okay. We can fix this up to make it better theoretically. The main thing here is the idea of looking at things that are close together in the sense of momentum space, combining them into more complicated objects, and iterating that procedure until we're done. So there's a long list of improvements, things known as the Cambridge algorithm, the Durham algorithm, KT algorithm, in E plus E minus, but since we're mostly focusing here on LHC physics, I'm going to skip over all of those ideas and go to sort of modern Hadron Collider. Jet algorithms. So first of all, in a Hadron Collider, we don't actually know where, in a sense, people tell you that the LHC is a proton-proton collider. But really, you should think of it as a parton-parton collider. And to some extent, you can even simplify things at low PT to think of it as a gluon-gluon collider. So what we're actually doing is, and we'll come back to a review of the parton model in a few minutes, but we're pulling one gluon out of one proton, one gluon out of the other proton. We're colliding them to produce something. The something is, of course, one of the things we want to calculate. But the momentum fraction, the fraction of the proton momentum that each of these gluons is carrying, is not 1. It's some relatively small number. It might be a 10th, might be a 20th, might be a 100th. Moreover, it's not the same for those two gluons. So there's a boost from the center of mass frame along the beamline, and that boost is unknown. It's something that we can't recover experimentally because all information about that goes back down the beam pipe. So we have to use boost invariant variables. And to do that, we can define a transverse momentum. So assuming that we actually have a track and that we can measure the momentum directly, well, then it's simple. We can simply take the angle with respect to the beam and multiply the momentum, the absolute value of the momentum, by its sign. If it's a neutral and we only really have deposition in the calorimetry, then of course we have to assume that each tower is massless and then extract the momentum from that. The other thing we want to do, so this is what replaces our notion of the momentum or the energy of a particle in E plus E minus. It's really the transverse momentum, and you should think of them as being interchangeable when you're going from E plus E minus to a Hadron Collider. We're also going to define an angular measure, and instead of having just some kind of cone size that you might use, just a pure angle around some center that you might use in E plus E minus. Of course, here we have to make it boost invariant, and so the natural thing to do is to replace the longitudinal angle by the rapidity. So we take the rapidity difference between two particles, and we take we average that in quadrature with the azimuthal difference between the two, being sure, of course, to take it the short way around and not the long way around. And this is the delta R variable. It's kind of the cornerstone of all measurements in a hadron collider. So there are basically two types of algorithms that have been employed. There are other kinds one can think about, but there are two types that have been actually employed at hadron colliders, and one are the so-called cone algorithms, and the other are the iterative algorithms. And the algorithm that is most popular with LHC experimenters is an iterative algorithm that basically looks like a cone. So it combines the nice features of both of them. So to understand what these algorithms are doing, again, not in great detail, but just to have enough of a feeling so that when I say a jet with a certain radius, then that'll evoke the right mental image. Then we should unroll the detector again, so we have rapidity running along the beam axis. We have the azimuthal angle, which I've unrolled here, going along here. And we're going to draw circles. So that's basically a circle of constant delta R. We're going to draw these circles in the plane. And the cone algorithm basically says that we want to identify all the circles which are of a given radius and move them around so that we have at least a certain minimum PT. We sum up all the towers and all the tracks inside the cone, and that gives us an estimate of the energy. And we want that energy to exceed some threshold, which we're going to call PT min. Now, in a cone algorithm, of course, you can have situations where these circles overlap, and then there are procedures for splitting the energy and the overlap between the two circles. So at the end of the day, in fact, they're typically not exactly circles, but they end up being pretty close. So the parameters of a cone algorithm are going to be the PT min, and it's going to be the delta R, or just which is really called just the R. And at the LHC, these things are typically, depending on the particular study that's being done, it might be something like 20, 25, 30, 35 GeV. For special purpose studies, you might boost that to 50 or to 100, but this is kind of the typical number that you'll see. These numbers are actually not much higher than they would have been at the Tevatron, even though the energy of the collider itself is much higher. The R's in the cone algorithms typically would have been 0.7 or 1 at the Tevatron, and now they're going to be 0.4, 0.5, 0.6, 0.7 at the LHC, and for reasons which are very much a mystery to me, the one experiment has chosen these two and the other one has chosen these two. There's unfortunately no overlap, so you can't compare numbers directly from one experiment to the other. And of course, as theorists, you have to do the predictions for each of the experiments separately. These are probably the ones that are the most frequent, happens to have a good set of properties with respect to confusion arising from hadronization. So the iterative algorithms are kind of a modern, very much refined version of the Jade algorithm. And here again, one introduces a distance measure between two objects. And it's now given not in terms of a dot product, but in terms of a minimum of 1 kt raised to a certain power, and the other kt raised to the same power. And it's multiplied by the angular measure divided by some normalization factor. So this is, in a sense, in a small angle approximation, it's like the pt of one of the partons with respect to the other. That's the way to think about this. We also introduce a measure of a particle with respect to the beam. That's just going to be its transverse momentum raised to that same power. Now, without going through the whole history here, then there are essentially three cases that one can think about: minus 1, 0, and 1 for this power p. Sorry about any confusion between p and momentum. And the traditional one, the so-called KT algorithm, is when you take p positive. And that was something that was tried out at the Tevatron, and it's an algorithm that has very nice features from a theoretical point of view. But if we go back to our picture of the plane, you tend to split the plane up into jets, but the jets would have very ugly kind of distended shapes. And experimenters didn't like that. That's not just an aesthetic judgment. It means that it's hard to do certain kinds of corrections. It's hard to estimate the corrections due to linking from the quark-gluon to the hadronic picture, the so-called hadronization corrections. And I also think that people at Tevatron didn't really give it a serious enough go. The 0 is something known as the hadronic Cambridge-Aachen algorithm. I don't want to really talk about that. The one that was invented by Gavin Salam, Matteo Cacciari, and Gregory Soyez, which no one had really thought about before, was the fact that you could also take this power to be minus 1. And remarkably enough, it doesn't match the intuition of how QCD forms jets, but remarkably enough, it has excellent properties from a QCD perturbative and logarithmic point of view, from resummation of logarithm, and it tends to produce jets which are basically circular. So the experimenters like that. It's very nice from the point of view of a lot of experimental systematics. And the so-called anti-KT algorithm, which is this choice p equals minus 1, is the one that is probably the most commonly used at the LHC, and that will probably stay true for a while. Let's see if I have, yes. So let's go back to our picture here. And these are, in fact, as far as I know, anti-KT jets. So what happens here is that we've run through this iterative procedure, and each of these towers has ended up getting clustered according to this rule. You seek the minimum of these objects, and the one difference in the hadronic case is things can also get clustered with a beam as opposed to with each other. And when something is clustered with the beam, then it's added to the list of protojets, and if it has a sufficiently large PT, then it will in fact be considered a jet. So here you can see that, first of all, you have these circles, but you can see that if you change the size of the circle, then you might end up, for example, combining these two objects into a single jet. Now, as it so happens, that would look like an object that has two lumps in it, but QCD jets can have that structure. Also, as you change the jet ET min, then some of these might be considered jets, or some of them might fall below the threshold to be considered jet. So you cannot look at an event and say this event has 5 jets or it has 6 jets. You have to know something about what the resolution parameters, what the jet parameters are. So this particular event might have as many as 9 jets if you have a very low PT, or it might have as few as 2 if you raise the PT to be sufficiently high. And that's an important point to think about, and it'll make a little bit more sense from a theoretical point of view when we get back to the consideration of infrared issues. Yes?
Is that the picture you had before as well?
It might have been the same picture, yeah. I might.
Based on 8 jet events.
So the number of jets depends, as I've said, on the particular cuts you're using. And the cut that they may have chosen might have said that the 2 smallest of these clusters, or the 3 smallest of these clusters, fall below the jet PT min. And so they don't count as jets. They're just radiation that goes into the event. From a theorist's point of view, they're in fact part of the corrections to the naive picture that you might have had of each of the jets corresponding to a single outgoing parton. So let's in fact, so are there, again, this is not something I've gone through in detail, but are there any questions at this point about how you should think about jets and sort of the very basics of the jet algorithm? Okay. So the next thing we have to look at is the question of how we do these calculations. How do we set up the framework to calculate the probability of seeing that event or other events or events with leptons in them, and how then to give the experimenters some information. And that's all done in the context of what's called the QCD improved parton model. And the parton model itself, of course, goes back to Feynman and Bjorkane in the 1960s. And even today, knowing all the physics and the experiments, it's hard for me to understand how people had such remarkable ability to see in the physics of the time that this picture would emerge. It's really a remarkable achievement. So we have our protons with the 3 valence quarks, but lots of C quarks and lots of C gluons. And as I was saying earlier, especially at moderate or low PT, most of the time what we're doing is pulling a gluon out of the 2 protons which are running along and which are colliding. And we're going to have some collision here at high PT, and stuff is going to come out. That stuff might be, for example, a quark-antiquark pair. We might also get, let's say, a Z boson coming out at some smaller PT, and that object might decay into neutrinos. So this would then show up as an event that has missing ET, namely you add up all the transverse energy that you see from the quarks and from other radiation, and you discover there's an imbalance, and that imbalance is ascribed, let's say in this case, to the production of a Z, which decays into neutrinos. Of course, these quarks can radiate as they're being accelerated away from the hard scattering, and the gluons themselves, as they're entering into the hard scattering and starting to sense each other at long wavelengths, can also radiate. So that's kind of the perturbative picture that we have in an event. There's a hard scattering, and there's some amount of additional radiation which we would like to compute in perturbation theory. And we have some set of observables we'd like to calculate. For example, you might want to calculate the distribution of PTs of the leading jet in an event. Or you might want to calculate the inclusive lepton PT in some class of events, in events with a minimum amount of missing ET and a lepton, a single lepton. So if we have some observable, we want to calculate its differential cross-section. And schematically, at tree level, we have to sum over all the different kinds of incoming partons. And we have to integrate over the momentum fraction of those partons. There's a certain probability, if you like, of pulling each of those partons at that momentum fraction out of the proton, one proton, or the other proton. And once we've pulled them out, there's some short distance scattering for AB to go into X. And we, of course, have to integrate that over the phase space of the final partonic system. And okay, if we were just to do this, we'd get some total cross-section. But we want to compute a distribution, so let's just put in a delta function. And whatever observable it is we're computing, we'll just calculate its distribution. So there have to be, of course, experimental cuts in here, and those experimental cuts are applied to the phase space. And in addition, that's also where we put in some sense, the Jade algorithm. There's nothing at this stage that tells you that you have to, that typically the way that you will do these calculations will be to integrate over the phase space of jets rather than the phase space of partons in a certain sense. But that is not exactly what you do in practice in the computer code, but it's conceptually one of the things that you're doing. So this is difficult. Those of you who are already doing this probably understand that. Those of you who either aren't or haven't yet started, then will learn that. And so, but on the other hand, the QCD component is very important because everything at a hadron collider involves QCD. So there's really no escape from this picture, whether you're calculating signals of new physics or backgrounds. You're always, whether you're trying to use measurements, let's say of W's and Z's for doing luminosity, whether you're trying to understand the details of the jet energy scale, everything is going to involve QCD. And that means that you have to work very hard because the strong coupling is not very small. So we have alpha S of order, let's say 0.12, is to be contrasted with the electromagnetic coupling, which, depending on what exactly you're doing, is somewhere in the range of 1 over 137 to 1 over 128. So it's more than an order of magnitude larger. The other aspect is that running is very important. So it's not at all sensible to say that alpha S at 10 GeV is alpha S of 100 GeV is alpha S at 1 TeV. These are all scales that you need to be thinking about at the LHC. And yet here, things are very, very different. So the change, so if you're going down from 10 down to 10 TeV, or then you're already past doubling alpha s. And as you go down, the changes are not as dramatic, but still you're getting down to significant changes in alpha s, let's say 20, 30%. And then alpha s, if you're going to be looking at some 10-jet process, is being raised to the 10th power. So even a 5% difference is already significant. The differences here are larger. So what does that mean? Whoa. Yikes. Sorry about that. So that means we have to be thinking about a number of different kinds of corrections. First of all, we're going to have very high jet multiplicity. As a homework exercise, you can go and calculate the probability of seeing 5 E plus E minus pairs at LEP2. It's not something you're going to get a grant to look for experimentally, I can assure you of that. It also means that each jet is going to have a large number of hadrons inside it. And it also means that higher order perturbative corrections are important. So the one thing that actually is not a real problem is the fact that we have these two different pictures, the partonic picture and the hadron picture. And the basic point is if we stick to what are called infrared safe observables, and we'll come back to see in more detail what that means in a few minutes, then we're effectively smearing over and summing over all the physics that happens at long distance. So all the different ways that the quarks and gluons can turn into hadrons, we end up summing over all of those. And then at that point, unitarity tells us that if we have that suitable averaging, that those pictures are the same up to power corrections that are not logarithmically enhanced. So up to corrections that are, for example, of order lambda QCD, which is a scale of order 1 GeV, divided by some very hard scale, which might be 50 GeV or 1 TeV, for example, depending on the particular observable that we're looking at. So we're going to have powers of these, and typically the power will be larger than 1. But in any event, these are corrections which are already well below the percent level. And percent level is something that we're quite far away from being able to treat in precision calculations. If we could get our measurements and our calculations to 1% uniformly, I think everyone would be ecstatic. So in the general framework of the kinds of approaches that we take, the kinds of ways in which we apply the parton model, then there are the general fixed order calculations. there are the so-called parton showers. And they're what I might call the semi-analytic and or resummation type of calculations. So these two classes are both numerical, generally numerical programs. Of course, they have analytic elements inside them. And they both allow you to do general observables. And that is true here as well. Theorists like these fixed order calculations because you proceed systematically in perturbation theory. The parton showers are based on leading log, or perhaps some elements of next to leading log. And so they're not systematic. And traditionally, theorists have disliked them for that reason. They're only approximate in an uncontrolled way once you go beyond the lowest multiplicities and once you go beyond the lowest order. The experimenters don't like the fixed order ones because you do not get events. And so you cannot feed these through a detector simulation, and you can only compare to experimental data and distributions. Whereas from the parton showers, you do get the possibility of doing an event-by-event comparison. And you can feed the output into detector simulation. So as a matter of practice, these parton showers, does the name Pythia mean anything to anyone? How many people have heard of Pythia? How about Herwig? Okay, that's good. So I'd say about half of the people. So these are programs like Pythia and Herwig and more recently Sherpa. So these are the experimenter's workhorse. And these are the codes that you would use for doing a measurement once you've actually understood and once you've done all the ugly stuff that goes into sausage making behind closed doors. And one of the interesting subjects of theoretical activity in recent years has been combining these two approaches, what's called matching parton showers to fixed order. And what that lets you do is combine many of the virtues of these two approaches. You can make the parton showers systematic, at least to some multiplicity. And what's understood really is how to do that matching to leading order in QCD. And the subject of active research is how to extend that notion of matching, of combining these two approaches to next to leading order. And so those of you who are working in perturbative QCD may very well end up working either on this kind of combination or on subjects related to it. So the ingredients that you need to do these kinds of matching are in fact the same ingredients that you need to do fixed order calculations. Namely, you need to be able to calculate these short distance cross sections, and those short distance cross sections are built out of amplitudes. And it's ultimately amplitudes that we're going to spend, you're going to spend most of this school learning how to calculate. The semi-analytic, as they suggest, they're devoted really to specific observables, and if you have some observable where you want the highest possible precision, combining all our knowledge of resumming leading logarithms with fixed order, then that's the way you'd go. And so it's also a useful cross-check for on certain aspects of these more general codes. So let's just see here. Okay, so that brings us, in fact, to the subject of, actually, let me continue down here. Of looking at a little bit more in detail at the different approximations that we have in fixed order calculation. So one of the things that was already alluded to is this notion of a renormalization scale. And it's something, of course, that in a basic field theory course you're taught you have to have a scale at which you define a coupling. That's true in any theory. It's true in QED just as well as in QCD. And you probably learned in that course that the QED coupling does evolve, and there's, if QED were the theory of the world with nothing else going on, and at some very, very high scale there'd be a Landau pole and the theory would cease to make sense, but in fact, being mortal humans living way down at low energy scales, we don't have to worry about it too much. Well, if you want to do precision physics at the LHC, then you do have to worry about it. So we needed, of course, to define the coupling and physical quantities should be independent of that scale. So exactly how you define it doesn't really matter. In other words, if you were able to calculate the mass of the proton, for example, well, the mass of the proton shouldn't really depend on how you define alpha s. The problem comes that when you actually do perturbation theory and you have to then truncate at some fixed order, then truncated perturbation theory leaves observables which are dependent on the scale mu. Mu r or just mu. And in general, the dependence that one finds is something like the first missing order multiplied by some logarithms. So we have to think about we know that we want to calculate in perturbation theory, so we're going to have some observable. For example, we might be looking at the PT distribution in W plus one jet events. So we produce W's along with a single jet or more jets, and we look at the distribution in PT of that leading jet. And more generally, any observable that we're going to measure has some power series in alpha s. And the coefficient of that first term is our leading order prediction. And we can now, of course, continue on to higher order in perturbation theory. There are actually people in the audience who have worked even beyond the next to leading order, and that's certainly something that will be of increasing importance in years to come. So, strictly speaking, sigma, of course, the sigma that appears there includes powers of the coupling, depending on how many partons are involved. I've removed those powers and I've written what's left over as sigma. So there's something special about the first term in this series, at least in the way that I've written it. Does anyone spot that? There you go. So this is one of the issues that confronts us when we look at some prediction at leading order. And what we can get out of that are basic shapes of distributions. So if we have some distribution that's very rapidly falling, or let's say some rapidity distribution that's more moderately falling, we're going to get that basic shape out of a leading order calculation. But we do not get a quantitative prediction. And moreover, we also don't get any sensitivity to the inner structure of jets. Why is that happening? Well, suppose that we're looking at the simplest process we can actually imagine looking at in QCD, namely two-jet production. So over here, I go back to my partonic picture, and I get rid of the Z. We just have a quark-antiquark pair, and there's maybe some additional radiation coming out. Well, the very lowest order that this process shows up in perturbative QCD actually doesn't have any of this radiation. We just have the two quarks coming out. So one of the things you can see right away that's a problem is the fact that suppose I unroll the detector plane as I did earlier, and I draw these circles, or I take the circles that would be effectively drawn for me by the anti-KT algorithm. As I change the size of that circle, nothing happens. I just get the same events. I would compute the same cross-section. The reason that's happening is that there's no additional radiation. There's no approximation to the inside of the jet. So that's one kind of problem that arises. The other kind of problem that arises is precisely the fact that, well, I've told you it shouldn't matter what I pick to be mu, but if I vary mu up or down, it's going to change this factor. It's going to change alpha s. This factor is not going to change. So my quantitative prediction is going to change up and down. Now, you know based on general arguments in field theory that precisely because these logs are going to be typically logs of mu divided by some physical scale, that if you're looking at two jets, for example, with a PT of 100 GeV each, you know that it's probably not sensible to choose mu to be 10 GeV. It's also probably not sensible to choose mu to be 1 TeV, because you know that on general grounds in field theory, and there's nothing to do particularly with QCD, you're going to induce these logarithms that have the ratio of those two scales. And clearly, if that logarithm gets large, all of a sudden, alpha s times the logarithm is not a small number anymore, and perturbation theory is basically broken down. You can do that even in QED if you take the scale to be many times the Planck scale when you're trying to compute some E plus E minus annihilation, let's say, into mu plus mu minus. So that is not special to QCD. What's special to QCD is that you can't just eyeball it. You actually get a significant difference even just from doing ordinary calculations. And we can take a look at that in some of these plots. And this is actually probably the first plot that I'm showing you where these techniques that you're going to be learning this week, or for those of you who already know them, going to be reviewing, have actually gone all the way and done collider calculations and have been used for physics. So this is actually a plot of the dependence of Z production in association with some number of jets. And it's a plot with respect to an unphysical parameter. It's this scale variation that shouldn't actually matter. So in fact, if we were doing an exact physics calculation, everything that you see here should just be a flat line, because there should be no dependence on an unphysical parameter. This is a physical cross-section. You have it. It's even in femtobarn, a physical unit. So what are we looking at? Here we're looking at the Z, let's say, as decaying into an E plus E minus and then picked up by the code or picked up by the detector. And there's one or more jets. And here we insist that there be two or more jets. And here that there be three or more jets. And what do we mean by a jet? Again, it's applying the anti-KT algorithm. And we're insisting that, in this case, that the jet cone be 0.7. So 0.7 is what's normalizing that distance measure that you saw earlier. And we're insisting that each jet have a transverse energy of at least 30 GeV. There's also some cuts on the lepton, but never mind that for the moment. So the variation you see in blue is what happens when you're looking at a leading order calculation. And the variation you see in black is what happens when you go to a next to leading order calculation. And the key point is that you still have, of course, the dependence on the scale inside the alpha s when you go to next to leading order, but the cross-section itself also depends on mu. And remarkably, it depends on mu in such a way that it doesn't flatten the curve out completely. That would be too much to hope from just one extra order in perturbation theory. You know, after all, that there's still going to be now alpha s to the n plus 2 times logarithms that are going to spoil the exact flatness, but it gets closer and it stabilizes. So we can see that there's a very rapid variation. Again, if you just have a single jet, single power of alpha s, might be something you're willing to live with in some reasonable range. Let's say you go up by a factor of 3, down by a factor of 3. That's not clear where exactly in that range you should pick the scale. Moreover, there's not, in general, in these complicated events, a single scale. There's, let's say, the PT of the Z, the PT of one of the leading jet, things like that. Another thing you can see, and that's, again, no surprise, that as you increase the number of jets, the variation at leading order becomes stronger and stronger. And that's just a reflection of the fact that there's a variation of alpha s, and you're raising it to a larger and larger power. And of course, we're interested ultimately in not just in 3 jets, but 4, 5, 6. You can see that even in a reasonable range, you're all of a sudden, your prediction here is varying up and down by a factor of 3. So what kind of a number is that? You tell your experimenter friend, well, you know, I can tell you within a factor of 10 what this cross-section is, but I want you to see a 5% deviation and tell me if there's any new physics. That's not very serious. So if we take the ratio of those two things, we can see that as the number of jets increases, the significance, the ratio of this stabilized next to leading order calculation divided by the leading order calculation is getting steeper and steeper. So this stabilization is getting more and more important. So it's when we go to next to leading order that we really get our first quantitative prediction. And typically across a very wide range of processes, very wide range of number of jets, we can expect, experience suggests that these are accurate to about 10 to 15%. Maybe some better, maybe some a little bit worse, but that's kind of the typical level. And that comes about because the virtual corrections have a compensating scale dependence. The other aspect that I haven't showed you, but that I can give you a cartoon. So one of the contributions that one has are the virtual corrections. We'll see in a few minutes. So those are, if you like, loop corrections. You can think of them in that fashion. But there's also corrections where we radiate an additional gluon. And now, as you change the size of that circle, you might include the gluon or you might exclude the gluon. So now all of a sudden, that cross-section is going to acquire a dependence on the R parameter, on the size of the cone. And more generally, you're going to start to have the first sensitivity. You have a basic approximation to the structure of a jet. What about NNLO? Well, of course, if you add more orders in perturbation theory, things get better. So you're improving the scale sensitivity. In other words, you're reducing it further. You're improving the approximation to jet structure. You're getting into the region where you can do really precision predictions where you can hope exactly where we get remains to be seen because there's only a limited number of these calculations that have been done to date. But I think one can hope that we will get better than 5% so that any theoretical uncertainties will be less than whatever the experimental uncertainties are. And also from a pure theory point of view, we can much better understand our theory uncertainties. And that in itself, I think, is going to be a very, very valuable output of these calculations. And this technology, certainly as far as high multiplicity, multiple jets is concerned, is all still in the future. Let me just stop here for a couple minutes and see if there's any questions thus far. We've had a couple during, but if you have anything else, now's the time to speak up. If you think about a question later, then ask it later, and we'll come back and answer it then. Otherwise, let me just continue on for a few more minutes, and we'll actually pick up with infrared and collinear safety at the beginning of the next session. Yes?
So you said the dependence of the renormalization scale is dependent on first missing order and the logarithms are dependent on which scale?
So, I mean, the precise logarithm that you get, of course, depends on the calculation that you're doing. So what I'm trying to give you here is kind of the general flavor of the logarithms that will arise. And it's also complicated by the fact that there are infrared logarithms in which mu can also get mixed up in. So ignore that issue for a minute. Let's just focus on the logarithms that have to do with the running of the coupling. They're going to involve the renormalization scale mu. Obviously, the argument of the logarithm has to be some dimensionless quantity, so there has to be some other scale that's involved. And that scale is going to be a typical physical scale of the process. So if you're thinking about it from a field theory point of view, you might say, well, it should be one of the invariants. So it might be a parton-parton invariant. But in fact, from a different point of view, if you're saying, well, I should work in boost invariant variables, then it's typically going to be a PT squared of a jet. That might be another example. And right there, you can see that that's a little bit unclear what exactly the precise number is, because, yeah, those things are of the same order. They're not going to differ by 10 to the 7th or even by 10, but they're not numerically identical either. So there's an ambiguity of a factor of square root of 2 or something like that. Does that answer the? Okay. So let's see what it is. So we know that leading order is sort of the basic starting point, because if anything else, before you go to a higher order in perturbation theory, you've got to go to a lower order. Yes?
Are these corrections related to higher groups or higher point entities?
The answer is both. And the precise way and reason is what's coming up. So if at the end of about 20 minutes into the second lecture it's still not clear, definitely stop and ask me again. So we know that to do, so NLO here is not a luxury that is just there to improve our precision. It's there to get a basic quantitative handle on anything we're doing. And that really comes into the parton showers as well. I mean, parton showers are a very useful tool for a lot of purposes, but if you're actually going to be doing measurement physics with them, you have to have solved this next to leading order matching question, which is, there's a lot of proposals and people have codes and things like that, but it's not yet a closed subject. So let's continue with this example of two-jet production and ask ourselves, what do we actually need to calculate in order to produce it? Well, we of course need the parton distribution functions, and we need those to whatever corresponding order we're trying to do a calculation to. In fact, typically, you might think that if you're doing a leading order calculation, then you actually should take alpha s to be constant. That's kind of what a tree-level running would be. But that's clearly crazy. So what you do is you actually take a one-loop running in LO, two-loop running in NLO, and so on and so forth, and the corresponding parton distributions would have the same running, same evolution, and same running put into them. So that's something that you ask James Sterling or the Italians, Stefano Forte and his collaborators doing NNPDF, and they give you some black box, which you hope is correct. So now, and these are in any event process independent, so once you've done them once, then you just apply them. What we need to do as theorists is calculate this object, calculate the short distance cross-section. And what ingredients do we need in order to do that? So let's think about two jets, two-jet production. Well, and let's, for the moment, just focus on the gluon initial state. So what we need is to calculate the amplitude for, let's say, two gluons going into two partons. Well, that could mean two gluons or a quark-antiquark pair. So I'm implicitly thinking in the back of my mind about quarks here, but for pedagogical reasons, for a lot of what I'm going to be saying in upcoming lectures, I'm just going to talk about gluons. So we're calculating the amplitude for 2 gluons to 2 gluons, and then of course we're going to square that. That gives us the leading order contribution to the short distance matrix element. And of course, we all know that you could actually calculate that by calculating nothing going to 4 gluons and crossing it. And I'm going to completely ignore any distinctions of crossing. So you should tune your ears to be completely crossing invariant. And you'll have a half-hour coffee to do that if you haven't done that already. So I'm going to fill in the circles here to indicate that what I mean, even if this is not actually the way that we're going to do these calculations, what I mean is that this is the complete 2 to 2 amplitude. So it's the sum of all Feynman diagrams. It's the sum of all Feynman diagrams which have 4 external gluons. I sum them all together by some means or another, and I square that. So that's the leading order contribution. Of course, if I'm going to do an NLO calculation, then I need first to have done the leading order contribution, so I need to have calculated this. And then I have, there's actually 2 different kinds of contribution that I have. So I first of all have an interference of which are the virtual corrections. So whereas this was the sum of all tree-level diagrams, this is now the sum of all one-loop diagrams, again, with 4 external gluons. You can think of it as 2 to 2, or you can think of it as being nothing goes to 4. The crossed version is really conceptually a little bit better to think about because there's no asymmetry between the different gluons. These are the virtual corrections. And in addition, remember that there's this radiation which might or might not get included. We also need to compute amplitudes that have 1 additional gluon. And again, this is the sum of all tree diagrams, but now instead of with 4 external gluons, with 5 external gluons. And then we need to square that. You can see that these are all of the same order in perturbation theory, because this is going to be, this is alpha s squared, and this is going to be alpha s cubed, and this again is g squared, and this is g squared times alpha s, so again, overall alpha s cubed. So these are all of the same order. There's 1 additional power of alpha s compared to the basic process. And the reason we need to include these different contributions we'll come back and review in starting in about half an hour. So let's stop here.